Hey, hello everyone, and welcome to another session of our 45 Minutes On webinar series by ASI. And today's webinar on how much sorting is required for a circular low-carbon aluminium economy. So I am Gabriel Carmona Aparicio, ASI Circularity Research Manager, and it is my pleasure to host today's discussion. This session is dedicated to exploring the transformative potential of advanced sorting in the aluminium industry. We aim to delve into how enhanced sorting can significantly reduce environmental impacts and prevent downcycling. So joining us today, there are two experts from Polytechnique Montreal, Professor Guillaume Majot-Battez from the Department of Chemical Engineering, focuses on quantifying the environmental consequences of technological choices. His research integrates complex systems analysis tools to shape environmental strategies, particularly in recycling and material recovery. His expertise extends to the life cycle analysis of lithium-ion batteries and electric vehicles, contributing significantly to the dialogue on climate change mitigation. We also have Dr. Julien Pedneault. His background is in mechanical engineering and has specialized in the circular economy. He has developed a keen interest in the prospective modeling of aluminium impacts and flows. His research under the guidance of Professor Magny and Professor Majot-Battez at CIRAIC has integrated various industrial ecology tools to understand the optimizations of end-of-life aluminium flows. Currently a research associate and scientific coordinator at CIRAIC, his work is key in navigating the complexities of recycling and resource management. So together, our panel will unravel the complexities of optimizing sorting strategies in aluminium end-of-life recovery and how this can potentially reduce greenhouse gas emissions by up to 30%. So over to you.
Well, we're very glad to be here. I'll start briefly by presenting the CIRAIC, our team, what we do, and then Julien will present most of the research. So if the CIRAIC, what's the CIRAIC? It's the International Reference Center for Life Cycle Assessment and Sustainable Transition. And what we are, we're very much a group that focuses on looking at problems from a systems perspective, looking at direct and indirect environmental impacts of our decision choices, our development, and our design of products and services. So the core of what we do is life cycle assessment, but we've expanded what we've been doing over the last 15 or so years to include more circular economy, material flow analysis, and looking prospectively towards trajectories for carbon neutrality. We're a group that with 5 professors from different universities that coordinate this. So we're largely based at Polytechnique Montreal, but we also have more into the management school at UQAM, and then a PFL in Switzerland and the HESSO. So it's an international consortium with very complementary skills. So, and if we look at the next slide, the way we're dividing, and this makes it very interesting, we have a sort of core research unit with industrial partners that fund this, and that makes the heart of our project, with long-term partnerships with the industry, which helps us, I feel, having very grounded research projects. And part of this is to fund research that's open with 40-some students, graduate students, and also research that is sometimes more targeted towards the need of the industry, that aims less for publication, and that is done with our analyst team that accompany our partners as they transition towards a more sustainable strategic plan and development. And along with that, we have other more publicly subsidized research projects with more specific projects and more specific mandates. So this diversity, I feel, helps us address today's topic, because we have questions of direct and indirect environmental impacts, but linked to this question of circularity is the dynamic material flow analysis and intercontamination of different materials and their fate, and optimizing it with an sort of operations research perspective over time. So as you can see, as is I'm sure is intuitive to everyone, you need very different perspectives and complementary skills for this. So we were very sort of lucky to get to tackle this, and it fit nicely within our sort of long-term research plan, which is basically to, on the one hand, look at, well, if we start on the left-hand side here, look at the environmental and socioeconomic impacts, both direct and indirect, and that requires us to look with sufficient detail at the different processes in our economic system, and sometimes we have to put more effort into detailing the processes that really matter, and sometimes we always want to present the entirety of the system, but sometimes we have to, of course, go for more approximations into representing the rest of the system. So it's very much about targeted efforts. And then on the right-hand side, we don't want to only assess the performance of products yesterday or today. It's very much what is their potential to evolve over time. But of course, the technology doesn't evolve alone. The rest of the economy is also changing, is also having its own trajectory. So we need to see that our solutions that we're proposing are robust to different potential pathways that the economy might take. So we want to reveal sustainable transition pathways, and we want them to be optimal. We want, with a operations research perspective, we want an optimization to reveal pathways that would be not only analyze predetermined scenarios that, oh, I thought about, I want to see if this works nicely, of the infinity of ways to transition, what emerges as something optimal and robust. And then, of course, and this is part of what we're trying to do today, is to build on this to support basically decision makers and dialogue with stakeholders to, and this is very much our central aspect of the figure here, to ultimately try to contribute to a more sustainable net zero future. So today's a nice case study, and without taking too much time to talk about the CIREG, I'd give it to Julien to carry on then.
Thank you, Guillaume, and thank you, Gabriel, for having us today. And it's a pleasure to present you the research, and part of the research I've done during my PhD. So I will start with a very wide context that I guess you already know about it, because you work in the aluminum industry. But maybe just a quick reminder that the carbon footprint of the primary aluminum production is very wide, depending on what type of electricity supplied the electrolysis process. But there's a way to reduce this carbon footprint by using some recycled aluminum. The carbon footprint is lowered a lot because the energy consumption is reduced, because we don't need to go through the electrolysis process, but simply remelting. And also, it's in theory infinitely recyclable, the aluminum, the aluminum material. So in a perfect world, it would be possible to just be in a full circular industry. But in reality, there's some limitation for the recycling. First of all, due to interalloy contamination, it leads to some cascade recycling. So different alloys are mixed together, and there's other type of contaminant, which lead to some downgrading, or the quality of the aluminum recycle can be more contaminated than the primary aluminum. So that's one of the limitations. To tackle this, there's some dilution and or sweetening that is made. So the addition of primary aluminum or primary other element flows in order to have the right composition of the different alloys. And finally, there's some researchers that have shown there's a risk of generating unusable surplus of recycled aluminum due to too much contamination. So that's kind of a threat that that may affect the aluminum industry in the coming years and coming decades. So that's lead us to our research questions. So how to reduce the environmental impacts of the aluminum industry despite the inherent limitation of its recycling system. So the way we try to answer these questions is we assume that it's possible to reduce the impact by moving towards a more circular system by improving the sorting and limiting the contamination. So that's kind of the end goal we decided to have in this research. So as you know, in the ideal world, we could we would have no contamination at all and a perfect sorting, but improving sorting is costly in terms of logistic, in terms of logistic, and there's also some limitation. So that's why we wanted to quantify the benefits of the additional sorting according to different sorting efforts. What I mean by that is, let's assume that we make no effort at all for the sorting. We mix all of the end-of-life flows. Here, all of the end-of-life flows, no matter where they comes from, they are just mixed together. That will lead to a big downcycling dynamic. It would be from this maybe possible to produce 1 or 2 aluminum with a lot of dilution, but it's not optimal. So we wanted to test what if we increase the sorting pathways. So let's say instead of 1, I decide to have 2 different sorting pathways. It would then be possible to sort. Some flows go into the first bin, some flows go to the other bins, and then we could create different type of alloys from the 2 different sorting pathways. We can even increase to 3 pathways, and so on and so on. So that's a bit of the first idea we had. But as you can see, the more we increase the sorting pathways, the more sorting possibilities increase. So we have more and more different possibilities in the sorting. So that's why we decided to develop an optimization model in order to identify the optimal sorting. So those different flows in order to have a optimal system in terms of environmental impacts. So which lead to our research objective is then to develop an optimization model applied to the sorting of end-of-life aluminum flows in order to minimize environmental impacts of the industry by combining life cycle assessment and material flow analysis data. So the first thing we did is to assess what are the future stocks and flows of aluminum. We did it in the previous paper and we did the dynamic material flow analysis on different aluminum alloys from 2015 to the end of the century with a global scale. So we modeled sector by sector to understand what would be the evolution of every sectors. And then we developed these different flows and stocks into different alloys and different alloying elements. But this work was only focusing on the demand and the end-of-life flows after its use in stock. That was the first step. And what we saw with this dynamic MFA was that we expect a growing demand for aluminum in the coming decades. And the saturation of stocks will only happen at the end of the century. Also, we saw that just in terms of demand and end of life, there was no major mismatch in the alloy composition based on our assumption. So it means that it would be possible to transform the industry towards a more circular system. But this model was incomplete. We were only focusing, like I said, on the demand and the end-of-life flows, and we need to understand how we can close the loop and which flows can really supply the demand. So that's exactly what the optimization model that I will present now will do. So our optimization problem is built this way. So we have a in-use stock that is needed for our societies. There's a demand of aluminum flows. This demand can be fulfilled by either some primary flows, some recycled flows. After his end of life, the stocks is transformed into end-of-life flows. Part of it go to waste due to insufficient collection rate. Part of it go to recycling. Then the recycling has been modeled with two different transfer matrices. The first one, represent the sorting. So there's different aluminum flows entering the sorting. They are mixed together according some coefficient transfer, and they are then sorted into different streams. Then the different streams are mixed together to produce different alloys or to produce very highly contaminated unused scrap. The third step of how we model the recycling system is the sweetening process. So there's some primary elements and primary aluminum that are added to these flows in order to have the exactly right composition for recycled flows, and these flows can be then can be used to fulfill the demand in competition with the primary flows. So that's like how the model is structured. But for an optimization model, we need an optimization function. So what we want to do, what we want to optimize. In our case, we wanted to minimize the impact of environmental impacts of the overall system. There's some emissions related to the primary production. There's some emissions related to the recycling activities. So the idea here is to minimize the overall impacts of the overall system. Then in the optimization problem, we have some constraints. In our case, the constraints are mass conservation. So at every stage, the mass entering is equal the mass as a output. And this is the case for the different flows, but also for all the elements in the different alloys. And finally, we have the decision variables. So the decision variables are like the parameters that the solver will find the optimal values in order to meet the objective and to respect the constraints. So in our case, it's the coefficient transfer of our two matrices, the sorting and the remelting matrix. And we solve this problem different time according different sorting effort. So we test what if we only, like I presented in the context slide, what if we have like only one bin, everything is mixed together, what if we have 2, 3, and we solve the problem from 1 sorting pathways to 8 sorting pathways to see what are the benefits of increasing this number. So a bit to wrap up what an optimization problem is and what's my problem. The idea is to find what are the optimal sorting we can do with the different flows, and what are the optimal sorting, I'm sorry, in order to minimize the overall impacts of the system. So with our scenarios, we also develop different scenarios in terms of dismantling. So our base case is simply that all the aluminiums from one sector are mixed together before being sent to the recycling. So it means that like there's a bit some contamination before even entering the recycling. So let's say that like we just get, it means that like we get all the aluminum for cars industry, everything is shredded and then sent to recycling. The other scenario is a bit more optimistic, is a full dismantling scenario, meaning that all the alloys, no matter which sector they comes from, they are mixed together before being sent to recycling. So it assumes that like it will be possible to know all the alloys and to group all the alloys together before being sent to the recycling. We also compare like an ideal sorting case. So this is in order to see the difference between our base case and a very ideal hypothetical case where there is no ideal sorting and there is no contamination at all. So that's we use that as a like to see the performance of our system in comparison to ideal case. And also we also test what if, because we on the base case we use some like average collection rate. by sector, but we also test what happens if we have like a 100% collection rate in order to test like what's the consequences of improving either the sorting, the collection rate, or the dismantling on the environmental impacts, because all of these parameters have an impact on the environmental performance of the system. So that's kind of these are the different scenarios we study. So we'll now go into the results. Okay, so as you can see here on the graph, if we look at this dotted line, the small one, it's with the right axis. So it's the overall demand of aluminium over time. So as we can, and this comes from the dynamic MFA we did before. So as you can see, the demand will like increase until the end of the century. On the left axis with the other lines, the colored lines, we see that like it's the environmental, it's the emissions, the annual emissions of the overall system based on different number of bins. So different number of sorting pathways. So the red one here is what if like there's no sorting at all and everything is mixed together. So as you can see, the environmental impact kind of increase proportionally to the increase of demand. If we look at the other lines, by increasing the number of sorting pathways, we see that like it's possible to decouple the emissions to the demand. And another interesting conclusion is that like even if we increase more and more the number of sorting pathways, even if we increase the sorting and increase the sorting, there's no like improvement in terms of environmental impacts if we from four bins, four pathways. So that's one of the, I think, interesting conclusion. One thing we can see in this graph is that even with the optimal and like 4 different sorting pathways that are optimal, we're still far from the ideal sorting. So there's some contamination because we have the no dismantling case, meaning that there's already some contamination before entering the recycling. So I will now present the similar graphs, but like with the full dismantling scenarios. So as we can see, the environmental impacts are even lower because there is less contamination and the recycle flows can substitute better the primary demand. So we can reduce the primary production and fulfill the same quantity of demand. And what's interesting to see is that this time the minimum is reached with a number of 5 bins. So with the 5 different sorting streams, it's possible to reach the ideal sorting case and to very decouple the environmental impacts with the primary demand. And finally, we looked also, here is the result for the full dismantling plus 100% collection rate scenario. So as you can see, the environmental impacts, even it's like a very hypothetical case, the environmental impacts are reduced even more, and the sorting becomes more and more important if we have a better collection rate. This is explained by the fact that like if there's more material that can be recycled, so and if we really want to supply the demand with this material, we need to avoid as much as possible the decontamination, so need to have a better sorting. So what I've presented so far is very like high level results, like the impact of the overall industry, but it was also possible to see what's happened like for the sorting itself. So we developed some Sankey diagram like this one for different year and for different number of bins or different scenarios. Here is the one with the 2050 year with 4 bins and full dismantling. So the conclusion we can have with this kind of graph is that we can look like what constitute the different bins. So which material are mixed, which alloys are mixed together. So first of all, as you can see here, There's the first bin is mainly made of 6063 alloy that comes from the building and construction sector, and they're recycled again in 6063 alloy. So it's kind of give us the indication that like a closed loop with closed loop recycling for the building sectors can be close to the optimal that has been calculated by the model. For the second one, the second bin, we see that basically is the alloys from aluminum cans that are mixed together in order to produce again an aluminum for the can, which is an interesting conclusion because in many regions and many countries, the aluminum cans are already have their own recycling structure in parallel to the other end of the waste management. And finally, and the third bin is kind of produce the 6000 series. So there are other 6000 series, and they are a mix of what it comes from transport and also a mix of different other alloys, but they aim to, these bins must produce some 6000 series. And finally, our last bin, even in the optimal scenarios, there's still some unused scrap according to our model that comes from the cast alloy that are recycled, and there's too much contamination leading to some unused scrap. So that was like a quick overview of the type of result we can have with the model we developed. So now let's have open the discussions and see a bit the outlook before the Q&A. So in terms of limitation, of course, we did an environmental optimization. We haven't looked at the economical aspect because, of course, there's some logistic costs by improving the sorting. There's like there's different challenges in terms of economical perspective, but we only focus on the environmental optimization. Also, of course, it's a theoretical model, so we haven't looked like at how a specific recycling facility can work. We worked at a very global scale, worldwide flows, and so on. And also, we only covered the inter-alloy contamination. We know that like there's other type of contamination with other materials, but the model couldn't like deal with this type of contamination. But still, there's some learning to do with this type of model. First of all, combining material flow analysis and LC into an optimization model can guide a circular transformation of an industry. Other like interesting learning, to my opinion, is that no need to go like very complex and perfect sorting sorting behaviors, just having like between 4 and 5 bins and to make sure that the right alloys are mixed together and to avoid some mix between different alloys family that can be close to the optimal of the system. And we said that some closed loop for the building sector and the packaging sector could also be implemented in order to reduce the environmental impacts. And finally, as a outlook, we looked a bit at the dynamic between sorting, collection rate, and dismantling, but this can be studied further. We mainly focus on sorting, but I think there's a lot to do with the dismantling also. And some idea we had to reach this optimal system is by improving the traceability, that in this way we could like facilitate the sorting and we know like the composition of the different pieces and different material that are recycled. And finally, also it's possible to have an impact like at the design step by promoting like design that facilitate the dismantling and the recycling of what it's made of. So that's kind of that was the overview of my research. We can start the Q&A. If you want to see the paper that is we did on this research, you can scan this QR code, and otherwise, Gabriel, I'd give you the floor, I guess, to lead the Q&A.
Yes, thank you. Thank you, Julien, for that great presentation. Indeed, it was nice to see like the connection between some of the circularity strategies and how can they impact the aluminium industry potential to achieve the 1.5 degree scenarios. So it's nice to put together like these two sustainability priorities for ASI, and also it was nice to see in the highlights at the end like the importance of traceability to facilitate implementations of these kind of methods and strategies. So that was nice. So we got some questions from the registration page, and I would like to read some of them. So I would like to hear your insights about, for example, one question was, what key challenges does the existing aluminum recycling process present in attaining the necessary sorting standards for a low carbon circular economy?
I can try and answer. Guillaume, you can complete if you want. I think there's some main challenges. You know, for the recycling, the thing is the products that are going to be recycled, they are everywhere. So in terms of logistic, we need to go get the aluminum part and the aluminum products a bit everywhere in the world, while the demand and the stock is not necessarily at the same place. So that's one of the challenges, like to make sure that to collect everything, but also that what has been collected can really fulfill the demand in the same area. Otherwise, you need some like international trade, which is possible, which is already the case. But I would say that's one of the main challenges and also to know what type of alloy is made. Like I guess I know there's some technology to identify the type of alloy, but yeah, to my understanding, it's not perfect. So to go get all the aluminiums a bit everywhere and to make sure and to understand what it's made of, and that's one of the limitations to reach like an even higher degree of performance in the recycling system. Guillaume?
Yeah, just maybe as a more high-level complement to what Julien just said, and this is not only specific true for the aluminum sector, but if we think more globally, like a lot of the recycling systems that we have right now work fine. There is demand for the recycled secondary end-of-life aluminum. But they work well because right now we have relatively small amounts of aluminum being recycled compared to the total demand of aluminum. And it's a growing market. So there's a lot of opportunities to bring in primary aluminum to dilute any contamination. So we naturally have a lot of sweetening. But if we think in terms of having a very circular economy and that the recycling flows build up and become a more and more important part of the system, then we transition towards from a system where recycling right now works to a system where at some point it will not really work. There will be a mismatch between the alloys we're able to make from secondary source and the demand. And seizing the opportunity to shift to a higher quality recycling early enough and not wait passively until we have a problem, I think is a challenge. We tend to respond to when things don't work anymore, not proactively anticipate. So this is why it's so great that you guys are here. So that we see things before we hit a wall. The other aspect is there's a changing demand for secondary aluminum, right? For example, we know, and this is just one example, but we know that a lot of the demand for more contaminated cast aluminum, a big segment of that demand is engine blocks for cars. Well, the car industry is also changing more towards electric cars where there is no such thing as a block engine. So how does the demand for cast aluminum change over time is both something that we were challenged to quantify because, well, we could find different uses for cast aluminum, but it's something we need to be aware of that, yeah, maybe there is going to be a change in that kind of demand.
Okay, excellent, thank you. I would tie these two questions, one from the Q&A box, and please feel free to send your questions into the Q&A box. So first is, do you have any knowledge about the available sorting technologies in the market? Probably not you're fully aware of those ones, but if you have any insights for the audience. And I will tie it with this one, which is, was the modeling based on existing sorting technologies?
That's a very good question, actually. What we modeled was very, in terms of sorting, was very theoretical. So it was basically only alloys that are mixed together, no matter, like we assume, we haven't modeled like specifically one technology. I see that there's some, like the sorting technologies are not 100% efficient. There's some mistakes. So that would lead to either additional contamination. But in our model, we only focus, like we haven't modeled specifically some sorting technologies. And it's not like a field that I'm very comfortable with, I would say. To be honest, so I prefer to say that yeah, saying bad things.
I mean, optimization models are interesting like that, right? Where the fewer constraints you put on the system, the more they point you to, oh, well, this would be ideal. And what we would aim to do then in the next iterations is basically to add constraints, to add realism. But I think it's important to not limit ourselves to what is sort of necessarily currently possible, but point towards what we would want for a genuine circular economy of the aluminum sector.
Okay, great. Another question that we received in advance was, where do you believe industry actors should focus their investments to most effectively advance circular aluminum?
To my opinion, personal opinion, I think the traceability would be one of the key challenges to address in the future, because if we want to move, like Guillaume said, like more and more constrained sector with even a greater demand for recycle flows, and like the proportion of recycle flows that is getting bigger and bigger over time, it's important to have a better understanding of what is made, what these flows are made of, and how we can and how we can maximize the utilities of like the use of these recycle flows. So yeah, either like technologies to identify alloys or directly some traceability to get like a better knowledge of these recycle flows.
And it's a spectrum, right? At one end, we would want to be able to sort of identify all the different alloys that entering to a recycling phase and separate them. But at the other end of the spectrum, as Julien showed, sometimes it's just about coordinating, not mixing the aluminum that comes from the construction sector with the aluminum that comes from the cans and food and wrapping sector. So like there's also sort of low technological solutions that are more about management and coordination with waste collection authorities and so on, right?
Yeah, definitely. There's space, there's room for improvement in terms of the operational practices of the facilities. Definitely. Another question,
like Guillaume said, I think that if I
go
can
ahead.
just add, I think like to work as like different sectors would be also useful, because at the end, a specific sector will use kind of the same, more or less, aluminum families. So if we can, if like the different actors within one sector, like the transport sector, the building sector, or packaging sector, if they can coordinate better together, that will, I think it's one way to make a more efficient system.
Great. Another question, great presentation, thanks. Could you comment on how the industry partners in your research so far reacted towards your research results?
To be honest, it's like it's the first time we presented our research to like very industrial partners, so I have no feedback so far on this. So let me know today, I guess.
Yeah, that's a good point. So from today, it will be good to hear from our attendees their opinion about the model and how probably they could implement this kind of tools into their facilities. So yeah, that's a good point.
Yeah, the tool as we built in was not made like very for a facility itself. It can be adapted for sure, but it's more like to give some orientation of the overall industry. But yeah, it would be definitely possible to have the same principles and to apply it to a very more specific case or a specific like facility.
Great. Probably from a more methodological point of view, rather than are we talking about alloy sortation, like specific numbers, 3004, or alloy series?
I would say both, because like the input data we had for optimization model is the dynamic MFA we did before, and depending on like the data availability, sometimes it was very like a specific alloy number, and sometimes it was like other series in general because we had no better data to see. But like the way the model is built, we could like use even having we can run the result again with even better data or better specification of alloys, but it's kind of a mix of both depending on what was available in our dynamic MFA.
I want to clarify one thing though. We tried to track the aluminum alloys with as much detail as possible, right? But when it comes to sorting, for example, when Julien presented the no dismantling case, we showed the different alloys that were present, let's say, in the car shredded scenario. But in that case, because it was all together, that sorting scenario sent all of these basically to the same bin, right? So so depending whether it's dismantled or not dismantled, we are able or not able to physically separate some alloys or not. So we always track them all, but it's not not every scenario assumes that we have the ability to separate them to such a high level. So this is something we like Julien said, you know, there's an intercontamination before it even reaches the sorting. Some objects are just made of more than one alloy, basically. So if they're not dismantled, the object just goes into that one bin there because it comes from a certain sector of the economy. Otherwise, it would not be very realistic.
Right.
And maybe one thing I can add, in our optimization model, there was no technology to remove alloy, like to remove one specific, no, not alloy, to remove one specific element within an alloy. So I know this kind of technology can exist. Sometimes they are not very efficient in terms of energy consumption, but that's something we could improve and to add some technology to remove some specific element within a batch and to reach other type of alloys.
Okay, thank you. I think we're reaching the end of our 45 minutes mark. So I would like to thank you all for joining us today, particularly, especially our panelists. A special thank you for give us some invaluable insights into the importance of sorting into the circular economy. And we hope all of you find the discussions informative and look forward to welcoming you to our next webinar, 41 minutes on opportunities and challenges on recycling and circular economy technologies. That's scheduled for the 13th of December. So we hope to see you there and have a wonderful day.